Hey everyone, welcome to lecture 2 of the LLM course. So I'm sharing the webpage here that we have for the course. So the topics are listed here, and I think the dates and times are listed here. And then so every lecture will have like a pre-lecture slide. So you can see lecture 1, we have the slide here. And then if there is any annotation, which we didn't have for the previous lecture, you'll find something, otherwise there's nothing here. And then we'll also have a recording also shared here. So you see the recording is up for lecture 1. So you can go check the recording as well. Okay, going back. Yeah, I think that's about it for now. We also have some, yeah, so today's lectures are here. So we'll actually continue with some of the material from the previous slide, and then we'll also get into some new material as well. Okay, so let's get started. Share this. So, last time we were discussing that, ChatGPT and LLMs are everywhere, and it's like everyday use case for many people for small tasks, or for if you're working in a company, you might use it for like have you guys heard of the GitHub Copilot? Yeah. So the Copilot is something that's getting used, or teams are being asked to start using Copilot actively because research shows that it improves productivity by 20 to 30%. So every company and every team is like, hey, come on, are you using GitHub Copilot? If not, start using it. So that's a very common use case for LLMs. In practice, those who've used it, is it like what would you rate the accuracy is like if you were to just get some code from GitHub Copilot and then just apply it right off the bat? Anyone?
For me, when I use it to actually complete something complicated, I feel like it's not that good, especially compared to ChatGPT, for example. But when it comes to kind of like the redundant stuff, it helps speed up a lot. Or just hitting tab and just finishing a bunch of redundant code. Very
Yeah.
useful.
Yeah.
Yeah, that's the
Even better than a purely discriminative model like BUT. So GPT and then the APIs, we see these APIs, and then Claude is like the foundation model, and Anthropic is the API, and then Stable Diffusion is the foundation model. And then you have DALI, Midjourney, or the API sitting on top that get exposed, right? So say, how does Midjourney work? How does DALI work? You go back to Stable Diffusion. So Stable Diffusion is the underlying foundation engine or model that's driving these APIs, right? That could be packaged in a little bit different ways and fine-tuned in different ways, but the essential foundation model is here. So just differentiating foundation models from APIs here. So for Stable Diffusion, we would say it's a pre-trained model, it's a foundation model, and it's a large vision model because it can handle images really well. Whereas Claude, GPT are large language models because they work with language and they're pre-trained. So anyone know the difference between trained models and pre-trained models? Why would you say it's pre-trained and then some models are trained?
It's like a transfer learning.
Who's this? It's like a transfer learning. Okay, can you even explain what transfer learning is?
When you have a model that is already trained, and then you freeze all the parameters that you have more information about, and then you take that and continue the training for your individual or specific task in your new model. Is that correct?
That's right. That's right. So a trained model is a model that's trained to do in traditional machine learning. A trained model is something you train to do a specific task, right? Um, so like if you had to discriminate different types of flowers or different types of species, and you have a model trained for that on those sort of images, it's good at that task. But that's a trained model. You have to train to do something. A pre-trained model is also a trained model. You have to train it, you have to fine tune the parameters and everything, but it's pre-trained in the sense that it can be followed up with some other task that that's kind of like a downstream task. And so that's where the idea of transfer learning comes up. For instance, LLMs are pre-trained models because they're trained on large corpus of data. They train on lots and lots of data. But then when you have a new task like sentiment analysis, you can still apply and get some results. You don't have to train again. You may have to fine tune, but that pre-trained model still serves a purpose to transfer the learning into the new application. So pre-trained models. And foundation is because it's trained on a large corpus of data. So that's why it's called a foundation model. So in machine learning AI, foundation models specifically refer to uh, really large models that would be trained on lots and lots of data, whether it could be text or image or videos. Just depends on the type of foundation model. And from the foundation, you start to branch off into specific fine-tuned models and uh, any downstream tasks that you want to address, right? Okay. And then yeah, so then we have the APIs, like we said, engines and foundation models are like the backbone, and we're going to spend time on that. So we're going to spend time understanding what the foundations look like, what are the components of foundation models, at least on some parts of the decoder and some parts of the encoder. And then we'll look at why are there so many stages to going from a foundation model to an API. An API, on the other hand, is a foundation model plus a bunch of extra fine tuning. You can have one layer, two layer, three layers of fine tuning, some with general purpose data, some with highly specialized data, uh, such as the ones that we used with RLHF, reinforcement learning with human feedback. And there could also be other hacks added in, other safety features engineered in, uh, to make sure that the API is safe. So there's a bunch of other things. So like you take the foundation, add a bunch of other things, and then you can get an API. And as an instance, like if you have Llama 3 as a foundation model, you can take Llama 3 and fine tune in specific ways, and then you can generate an API out of it. The API might do much better than just a vanilla version of Llama 3, but the foundation of that API is still Llama 3, right? So that's an example where you take something that's released in the public, for instance, Llama 3, and then you build an API out of it. Okay. So let's go back. So this is high level. Let's go back to some really basic questions, right? What exactly is a language model, right? Large language models, LLM. So LM starts for language model. So what exactly is a language model, right? So language models are scientific data-driven models that help machines understand language and patterns in sentence construction, right? And language models are, do you think language models are pretty recent in the research community? What do you think is the time frame that people started looking into language models?
The 1950s.
It's pretty early, right? And with some, rigor of or some algorithmic focus, I would say probably 1970s, 1980s is when you actually had algorithms to work with language models. But the most basic language model was as simple as, can you predict the next letter if I give you the previous letters of a single word, right? It's like just saying, like one is like saying, hey, in English language, what's the most common letter, right, of the alphabet that you see overall? What would your guess be?
C.
Letter A.
A. Anyone else?
E.
E. See E a lot. What's the second most common?
I think I.
I. So you can ask ChatGPT on this, and it'd say ETAOINS. So E definitely comes up at the very top. So across all possible words in all possible books, in all possible articles, from all possible sources on the web, um, maybe we don't even need to do that. We can just look at the dictionary, right? Just look at the dictionary of words and say, how often do you see E in any word? How often do you see any other letter in any word? And then E would rank at the very top. So this is like, if you, the most simplest language model is, can you even tell me what the most frequent alphabets are? And then you say, yeah, that's ETAOIN. That's like the simplest understanding of language is just the frequency. This is like unconditional frequency, right? Because it's not conditioned on anything, right? Now, if I say, well, if my first two letters that I've seen so far is um, T and H, what would be the third letter that's most likely to follow after that in English language? And what would your guess be?
E.
E, right? E is a very good guess. So now this is a conditional understanding of language. I have a condition or I have a context. The context is I've already seen the letters T and H, and I'm asking what would be the next most likely letter that would show up. So then you'd say, okay, that's probably E. And this is the math behind this is, any guesses what the math that's used to describe this idea it would be?
Is it
Probability.
maximum likelihood or something?
Maximum likelihood, and even simpler. Like what construct and math can be used to capture this
Probabilities.
Probability distribution?
specifically within probability?
Conditional probability?
Conditional probability, that's right. So what's the probability of the letter E given that you've seen the letters T and H in that sequence? That's what, and then you would see that probability ranks higher as compared to any other letter in the alphabet, right? So the conditional probability would tell you what the next letter is. Now, this might seem very trivial, right? Okay, T and H, okay, E, sure, that's great. But even ChatGPT is doing that. Like as you ask a question and it starts typing, it is doing sophisticated probability computations, but based on data it has seen in the past, but it is still a probability, computation. And then it's very likely going to make a very accurate estimate, but then it's still like next word generation, next character prediction, next sentence prediction. It's still a probabilistic model that's actually being used to generate sentences and respond to questions that we ask. But it doesn't seem that way because it seems very accurate. So even though it's probabilistic, its probability distribution is very refined and very tuned to what it has seen, right? And so it looks pretty accurate. And even have you thought about it? Like if this is a question for all of us, right? If someone asks you, can you describe the weather in Seattle? Uh, what would you say? Like in a single sentence? Anyone?
Rainy.
Probably rainy.
Probably rainy. Suppose I ask you the same question tomorrow, would you say the exact same words that you used today?
Probably.
Probably.
Yeah.
And if not, what would be the different way to describe your answer tomorrow?
Cloudy.
Cloudy.
Maybe cloudy.
What if you had to use a sentence?
For what the weather will be like tomorrow.
Yep.
It's likely to be cloudy or likely to be rainy.
It's likely to be cloudy. So you can see, you can paraphrase this in many different ways, right? If I would say it's cloudy tomorrow. I think it's cloudy tomorrow. It's very likely cloudy tomorrow. I'm guessing it would be cloudy tomorrow. Yeah, depending on your mood and your uh, stress levels and how attentive you are, you might use different language. Isn't that true? But all of them convey the same meaning, isn't it? So it's the same thing, is even though ChatGPT seems pretty fluent in English language, every time you ask a question, you might see it as paraphrasing in different ways because it's still using a probabilistic model, just like we do, right? It's not like we've memorized all the answers to all the questions someone is going to come and ask us today. Hey, I know yours is question number 100, and let me just think, yeah, this is the answer. That's not what we're doing, right? Like we speak on the fly, we come up with construct sentences on the fly, and it makes sense, but it's not that you know everything that you're going to say beforehand. It is like based on what you've said so far, you might switch gears or you might continue down the path that you're thinking. So that's exactly, so we are, as well as humans, using probabilistic models, right? And so if ChatGPT were to do the same thing, it seems like a plausible way to do something intelligent with language. Does that make sense? If we think we're good and eloquent speakers, then maybe there's a way for AI to also get there and maybe even better. And that's what we are seeing like today. So anyway, it comes back to conditional probability. So that's what we were discussing before. The main construct from a mathematical standpoint is what's the probability of next character given the current set of characters? What's the probability of the next word given the current words that we've seen so far? What's the probability of the next sentence that you want to construct given what you've seen? So any which way you want to parse, or the next token, like if you're looking at a token level, right? Question?
Yeah, I had a quick question about this. Something that always confused me about this is, so why would the probability change given the same set of words or same set of characters? Why would the next word be different, you know?
So with probability, right, there's two ways to generate. One is like the max likelihood. What's the max probability word, next word? Just keep sharing that, right? So then would it change? It wouldn't change. But what's another way to use a probability distribution that you still make meaningful predictions, but it could be different every single time?
Is it like within a certain, I don't know, standard deviation or certain range of percentages, like a threshold?
Yeah, so this is something we'll go into details in a bit, but we would call it sampling. So even though you have like a very high likelihood of this particular word coming up, you might still look at the next close enough high probability word and then say, I will sample. So I'm not exactly going to play to the best possible probability. I might look around a bit and then I would sample. So when you start sampling, then you get variety. And so that's how you would generate different responses every single time, because you're sampling rather than picking the best possible, because your model is fixed, right? If you think of the foundation model for any LLM, the parameters are all trained and tuned. So it's all fixed out there. But what's changing is when you actually start to generate, you might sample from the top 5 candidates or the top 10 candidates, and that changes how the responses come out. So it's a probabilistic sampling of really good candidates. So we're not saying bad candidates, but there's like, instead of just picking the one best candidate, you take like 5 or 10 or 20 different candidates and say, from these, let me sample, and that's how the variations start coming in the responses. Yeah.
And Professor, how the context is included here?
In for an LLM or for a language
For
model?
for LLMs.
Oh,
LLM.
LLM will come to it in a bit, how the context gets included. Yeah, that's a good question. But all the context, gets fed in as the initial data, initial thing. So let's say, for LLMs, just short answer is if you have a prompt, the prompt will have the context, right? It'd say, hey, this is a scenario. You remember yesterday we had this question, right? Here's what you're supposed to do. You're supposed to tag it as a positive, negative, or, neutral sentiment. That's the context that we are providing. Now given that context, you can ask questions, and there's ways that LLMs can preserve the context and then keep answering questions. Okay. So moving on, let's look at next word prediction. So we looked at next character, like THE. So here's an example of next word. I just got promoted. I'm feeling so. What would you say is the best possible prediction here?
Happy.
Happy. Look at that. Almost everyone is saying happy, right? That makes a lot of sense. So now the context is very, very clear because the context is not coming from just this sentence, right? It's coming from the previous sentence. The previous sentence has the context. And so as long as you can capture the context from here, you're going to say, I'm feeling so happy. Yeah. So that's a good guess. And so that's how any large language model is able to carry the context from not just this sentence, not just the previous sentence, but maybe even like 1 or 2 or 3 paragraphs or 3 pages before to know that, oh, this is where you're coming from. I should keep that in memory as I answer your question right now. Okay. So I'm feeling so happy. So that's the most logical conclusion to this sentence. Let's look at another example. I just checked my application status and it got blank. It's frustrating. What's the blank likely here?
Rejected.
Rejected. Where is the context coming from?
The same sentence. Or sorry, the next sentence.
Coming from the future,
Yeah.
right? So although you cannot predict the future, it's like I need to know the future to know what the present is, right? That's what this sentence is looking at, isn't it? So the previous one is an example of next word prediction task, right? If we have tasks in machine learning, this would be an example of next word prediction task. But this one is an example of random word prediction task or masked. This is an example of masked language model. You mask certain words in a sentence, and you might have to use the past and the future context to fill in for the present, right? Does it make sense? In this case, I had to look at the future to know, oh, it's frustrating. So that means your application got rejected. Okay. So this would be a masked language model or masked language task that's used to train machines to even predict in between. So you don't just have like a linear understanding of a sentence, but you can parse it in non-linear ways. You can break it up and say, oh, pick any random word, mask it, and I'll tell you what it is. So I really understand how sentences get constructed, right? Okay. So LLMs are language models that are learned from massive corpuses of text that are mined from the web. They're known to be sophisticated in understanding language and can be generative in nature, right? Are generative in nature, actually. So let's look at a brief history of language models. Like we asked this question, how far back do language models go? They go quite a bit in the history, but we're going to start tracking it from the time when certain algorithms came into play. So how did machines work with language before, and how do we do it now, right? So one of the earliest models that people came up with is based on the single cell neuron that's in our brain. So our brain has billions of neurons that coordinate in very, very sophisticated ways that we don't yet fully understand to make us as intelligent as we are, right? Or perceived to be as intelligent as we are. So, but if you take a single neuron in our brain and you want to mathematically model it, that's what we have here as a perceptron. So perceptron is a mathematical analog or equivalent of a real biological neuron that sits in our brain. And if you ask, what does a neuron really do, stepping aside from all the biology and all the other, chemical and biological processes that might happen, it basically takes in inputs through uh, these things called dendrites, and then it has a cell nucleus that does something with these inputs, does some chemical transformation, and then it passes it on through the axon terminals as output signals. So neuron basically is an input-output transformer. It's transforming inputs into outputs through some logic. And that's a single neuron, but then you have multiple neurons and then they coordinate together to do massive transformations every single second. Like right now, as we are having this lecture, millions of neurons are firing in your brain to ask questions, understand, parse, store, process, digest, etc., etc., right? So it's a real phenomenon happening every single second in our brain. So a perceptron is a mathematical model of the same, of the neuron. Very simplified. There's no, it's just a mathematical process, right? So Perceptron was one of the first models that was proposed in artificial neural networks. So ANNs, artificial neural network, started with the idea of perceptron and said, let's try using a perceptron and see how intelligent is it for day-to-day real-world tasks. Like, can it discriminate a cat from a dog? Can it do this or that? Can it, predict certain things? Can it predict whether, let's see how far can a perceptron go? And people found that a perceptron can only go as much. So then they kind of brought together multiple perceptrons, and then that became a feed-forward neural network. So that was the next innovation in deep learning, or pre-deep learning is just neural networks, right? So deep learning as such came about in 2000s when the compute power increased, the memory increased, that you can actually do heavy duty computations. GPUs came about that you couldn't do before with just CPUs or with the processing power that we had in 90s. So 2000s is when people started using the concept of deep learning, because you could actually train deep networks and not just shallow networks, which was a limitation in 90s, right? So perceptron led to feed-forward neural network. And then people said, well, I like the idea of feed-forward neural network, but it's just doing one task. It's just a single-use thing. Predict this or that. That's it, I'm done. But if I want to use it again and again, like, we talked about next character prediction. Like if you want to predict the character Z coming after JAZ, so that's like the next character prediction. We just spoke about it. Then people said, let's use this idea of recurrent neural network. It's a recurrent thing. You just stack it. You just use the same neural network, but then repeat the computation. So you pass in J, you get maybe A. You pass in A, you get Z. You pass in Z, you get Z. But this underlying network is it's just kind of the same here from here to here. Only thing that changes is the state. The state here is like a random initial state. The state here is some hidden state that's coming from before. So this hidden state captures the context from the past characters, right? So although the parameters here don't change, the context changes, and so the prediction changes. So this was one of the earliest examples of a generative model, AI model, and it's called a recurrent neural network, and it had a lot of issues. There was issues in training, there was issues in generation, there was like all kinds of issues happening with recurrent neural network, and it couldn't even get the context. It had a very short-term memory, so it was very short-term memory, right? So it really didn't get the context from like 2 or 3 sentences back. So there was an issue with RNN, and so to fix it, people came up with something. So what is the issue? Let's look at it. So one of the issues with RNN is it wouldn't even understand that there was something mentioned a sentence or 2 sentences before. Here's an example. Suppose I ask you this question. I just arrived in New York. In a few days, I would like to visit the city blank. What would be an example of a city?
New York City.
So you just arrived in New York City, and in a few days, I would like to visit the city, New York.
Wait, do we mean New York, the state?
Let's say city. This is a city.
Oh, okay. Oakland?
Oakland. But would you say New York City here?
No.
No, right? Because you just arrived. So that's the context. But RNN might still predict New York City, right? Because it somehow forgot the context and it likes New York, and it says, anything you ask me for a city, I'll say New York. So it just didn't somehow capture the context from just one sentence back. So to fix the issues with RNN, there was a model called LSTM, long short-term memory network that came about to fix the issues in RNN, right? So it can have a longer So as the name suggests, LSTM is long short-term memory, right? So it's a short-term memory. All these models had short-term memory, but can we make it longer? So that's why it's called the long short-term memory network. So LSTM fixed some of the issues because it had like a hidden state, HT, but it also had a cell state that was kind of a slow changing state. So that thing that came up one sentence before, two sentences before, that would fall under CT. It would change slowly, so you wouldn't lose context so quickly. But this HT, the hidden state, would change very quickly, and so you would forget. You had an issue of forgetting. You would forget what happened like one sentence back, and that was an issue with RNN. So the introduction of CT in this network help with making the short-term memory longer, right? And so LSTM, if you use LSTM instead of RNN, and you ask the same question, it would give a different city like Seattle, right? Instead of predicting New York City. Because the CT here would capture the context better. Okay, and then came LSTM with attention. So even before attention became popular with the paper, attention is all you need, right? That was a transformative paper that kind of started the advent of transformers. And then from transformers, the GPT, and from GPT, LLMs and ChatGPT and all the hype that we see today, it started with this idea of attention. So people said, well, if we can understand, like, what's an example of attention? Suppose, how many of us know more than one language or can read more than one language? Read and understand more than one language. So have you noticed sometimes when you're translating, depending on, let's say I'm translating from English to French or, any other language, right? English to Spanish. Suppose I'm looking at an English word in a sentence, you would have to know where in the sentence are you at, and then you would have to pay attention to certain constructs in Spanish, for instance, to know that, oh, so you're here, so that means I would have to say it this way. So you'd have to pay attention to a few things in the already constructed Spanish sentence, right? To know what's the next word in the Spanish that you have to fill it in with. Does that make sense? Like, as you're translating in Spanish, you'd have to keep paying attention to what you've already covered in the English language. So because the way you construct a Spanish sentence might be different from the way we do it in English. Does it make sense? So you keep paying attention, you keep going back to the English input sentence, and then you're like, oh yeah, I think we already covered that. So let's just focus on this. And where is this exactly in the English sentence? It's here. Okay. So that is the idea of attention, is as you're doing a task, in this case, machine translation, you keep paying attention to the inputs and making sure you're using the right information for the next thing that you're going to predict, right? So LSTM with attention came about, and it was doing much better than just using LSTMs for different tasks. And then transformer, the paper, attention is all you need, kind of transform the landscape by saying, hey, attention is going to be the key concept that we're going to use. We're going to use self-attention, cross-attention, all kinds of attention, encoder attention, decoder attention, encoder, decoder attention. So they kind of had different concepts around attention to say that this is going to play a big role in helping AI do much better at a lot of tasks, right? So as you can see, one thing led to the other. If you look at the evolution from perceptron, it's just a single neuron, right? If you look at the more recent models, they have like millions or hundreds of millions of neurons, right? So we've come a long way from just having a single neuron as a perceptron or one of our first AI models to having hundreds of millions of neurons, just like our brain. Our brain has like billions of neurons. And even for a simple task, you'll have to use quite a few neurons to do the job. So this is kind of the evolution, come a long way, right? And then the left part of this figure is very important. This is something we're going to revisit when we come into transformer theory. So we're doing a lot of high level right now. So this is not like, okay, you need to get everything today. It's just high level. So don't worry, we're going to deep dive into some of these architectures in like a few lectures, maybe like 4 or 5 lectures down the line. We'll again revisit transformers, we'll again, start to pick this apart. But at a high level, the left part of this graph or this figure is the encoding part, right? And the right part is the decoding part. So the decoding part is what led to GPTs, right? So people said, let's just use this part. Don't worry about this one. Just keep using this and then it'll do a good job. Aiden?
Yeah, so 2 quarters ago, I took a class where the professor had just mentioned something new that had come out about XLSTM. Do you have any thoughts on where that fits in? I guess it was relatively recent that it was put out, but do you have any thoughts on how it fits into this or experience with it?
So I don't exactly know which one you're referring to. Maybe you can share a link to that in the Discord, and then we can take it offline, or maybe if it's relevant, we can address it next time as well.
Yeah, I guess it's just an extended long. I'll put it in chat right now.
Yeah, you can put it in the Discord and we can come
Oh,
back.
Discord, yeah. I'll do that. Thanks.
Okay. Yeah, I think there'll be a lot of branches that are coming out of these. So, but I think I think this is something I would encourage everyone. If you find something interesting, you want to have a discussion, feel free to use the Discord for that. And we can definitely, some things that are very common and central we'll cover in class. Other things we can always cover in Discord or have a separate discussion on it, right? Okay, so transformers, and then we said, there's an encoding transformer, and BERT is one of the fundamental models for encoding and discriminative tasks. And BERT was one of the first models that came with pre-training and fine-tuning. This concept of pre-train, fine-tune started with BERT, right? Because it's sometimes, it takes a lot of time to train, and you don't want to keep training from scratch. It's like, hey, I have a new task, let's train from scratch. It's going to take X dollars and Y, amount of days to train, and let's just keep reinventing the wheel. So pre-training took away the issue with just reinventing the wheel every single time and said, hey, for certain common tasks, just start with the pre-trained model. It already has like a good starting point. No need to reinvent the wheel. And then fine-tuning is one where you just say, okay, I still need to fine-tune because I have a specific task in mind. That's the reason. So with less effort, you can fine-tune and get a good model. So this idea of pre-training and fine-tuning kind of started there. Also happened parallelly in computer vision. So computer vision also started around 2007, 8. People started diving into deep learning models, and they also started doing pre-training, fine-tuning. So the language and vision kind of went in parallel on this front, right? So we saw sentiment analysis in the last lecture, but before LLMs, BERT was the go-to model to do sentiment analysis. And also summarization is another task. Okay, so high-level GPT versus BERT. While BERT is purely about encoding and is called an encoding transformer, GPT is purely a decoder and is called a decoding transformer, right? Question?
Yeah, that was me. It was regarding the last slide, actually, when you were talking about fine-tuning and pre-training. I was wondering if you had any intuition on how that's changed as the model architectures have gotten more complex. Has fine-tuning become relatively cheaper in comparison from pre-training, or are we investing more time in pre-training to develop a certain task?
Well, certainly it's changed a lot. Like as you see with foundation models, pre-training is like the heaviest component, and it can be very expensive. Like training one GPT, like let's say GPT or even Llama type model, like just getting one version out can take $1 million. So if you have $1 million and you want to pre-train on your own, go for it. But that's kind of like the amount of GPUs and churning and energy. So it's not energy efficient. It's not, environmentally friendly for everyone to start pre-training. And it's not to mention the amount of money it takes. And so it's good that only a few companies and are actually investing in pre-training. It's good. And we have some of them are proprietary and some of them are open source, because otherwise we would have a big environmental issue with so much of CO2 getting released every time a new model comes out. So it's incredible. Like the amount of carbon footprint a pre-trained model can have is it's just simply incredible. It's like driving a truck every day for X number of months. Like that's kind of like the amount of carbon footprint that comes out. But thankfully, not everyone has to do it, and very few people actually have to do it. It just have to make it accessible to a developer so that they can fine tune it. So definitely, like with the foundation models, pre-training is like 90% of the time, right? But fine tuning still also has expanded in scope from simple fine tuning to like a bigger fine tuning and like reinforcement learning fine tuning and then the like task specific fine tuning and all of that. So I think with yeah, we'll talk about it. So we have LoRa fine tuning. So yeah, there's like different things you can do with fine tuning from simple to more complex. Just depends on your task. But pre-training is something that we don't do anymore for foundation models. You can still pre-train a BERT model, for instance, because it's a smaller model and you can do it. If you had a couple of GPUs, you can just do it and it won't cost as much. But yeah, I mean, maybe even small language models you can pre-train, which have much fewer parameters than like a large language models. So, but again, the question is, do you have a need for fine pre-training? That's something you need to ask. So if you have a completely new application and you think you'll do really well, and you have the resources and you have a lot of people who will consume it, that warrants pre-training. Otherwise, you're just reinventing the wheel and you might not even do a good job as existing pre-trained models. So that's another issue is, yeah. So hopefully that answers your question. Yeah, and you know, if you think about it, like with LLMs, right? They've completely changed the game. They say, hey, you may not even have to do fine tuning. You can just do zero shot, few shot, in context learning. So it's the in context learning is not even fine tuning. It's just passing in a few examples in context as you're asking the query and saying, hey, you may want to think about it this way. And then it's not really changing any parameters in the model. It's just giving it context to then respond better. And that might still do a good job for your end application. Like even things like prompt engineering with RAG, right? We're not doing any fine tuning. We're just saying, here's a source of data. I want you to stick to this source of truth. This could be a document, this could be a PDF, this could be a book. Use it as a source of information and then answer questions in specific ways with prompt engineering. So no fine tuning and no pre-training, but using the foundation models in specific ways, right? So yeah, the game has changed a lot since the advent of LLMs. So you really have to see what's your use case for fine tuning. I mean, at an industry level, you still want to do fine tuning for special tasks or a class of tasks, but yeah, we'll have to start with in context learning, RAG. If these don't meet your cut, then you can go to fine tuning. And you almost always never have to do pre-training unless your company wants to develop a LLM from scratch, right? Okay, so we spoke about GPT versus BERT, and GPT, you know, the evolution of GPT, we had, you know, GPT-X, right? So GPT, GPT-2, GPT 2.5, GPT-3, GPT 3.5, GPT-4, GPT 4.0, and then whatever is coming out from OpenAI, right? But the initial GPTs were not OpenAI; they were open, like Google had a hand in it. OpenAI, some of the OpenAI researchers were part of the initial papers, but then they took GPT-2 or 2.5 to the next level with GPT-3 and 3.5. And then that's where it became proprietary. But GPT, the original paper itself is kind of like open source and it's like out there. So, but what OpenAI did is they kind of took GPT to the next level with, so that's the key contribution that they made. So yeah, and so GPT are decoding transformers that are trained to predict the next token given the past, and they do a very good job at it. And like we spoke, like we discussed, that's how they can generate entire paragraphs that look logical, grammatical, and structured. So this was the key innovation. Like before, you would see all kinds of mistakes, like grammatical mistakes, repeated words, sentences not formatted right with earlier versions of GPT and earlier versions of like LSTM and RNN. They're really bad. And people said, hey, this is what AI is. It can't really get to making really beautiful sentences like humans do. But then somewhere it like things just changed, like GPT-3, GPT-3 just took off. And you're seeing like really beautifully crafted sentences that look like something a human would write or speak about, right? And that shift happened because of the massive amount of data that these models were churning, but also the sophistication of the model itself. Like GPT as an architecture had all the capabilities to be able to do this, and that's why we are seeing it happen, right?
So I was just actually going to ask that. There's kind of like that step function, like you mentioned, like suddenly they were doing these, very sophisticated responses. Do you think that's a direct result of like the proliferation of compute power and figuring out how to leverage like GPUs? And because I feel like the GPU leverage kind of happened over a few years, but yeah, kind of in the few years that
I
preceded.
think it's a combination of compute, data, and also like the layers of fine tuning. So without RLHF, like RLH, so if you look at that, I think we'll get to this when we go through the accuracy graphs. The accuracy graphs without RLHF and with RLHF are like striking, like there's suddenly a bump there. So definitely the fine tuning had a role. The massive amount of data corpus that these new set of foundation models started going through, that had a role. And the ability to actually train on them with massive amount of GPUs also had a role. So compute, data, and superior fine tuning and just the fundamental the goodness of the foundation model, which is like the transformers as like a good foundation to go for where we are right now, right? So
Thanks.
the combination, and you can see the combination come into play once we start looking at the numbers, which we'll do in a few lectures, right? Okay, good question. So some of this is still a little bit outdated, but like we might have more tokens now, but a lot of these models like the open models like Llama 2, they use like 1 trillion tokens. And think of tokens as like concise packaging of data. It could be like a subword or parts of words or something that is like, it could even be not a regular word. It could be some acronym or anything, right? Anything that can be used to construct sentences and respond to queries in a meaningful way. Obviously, you can crawl the web from Common Crawl, C4, GitHub, books. Like coding has its own tokens, right? Like you wouldn't see, certain words you'd only see in a coding language. You wouldn't see anywhere else. So they have their own set of tokens, books, archive, research. You would see tokens that come from research that you would never see in regular language, right? Um, so Wikipedia, Stack Exchange. So anyway, so different sources of data would generate different sets of tokens. And when you put it all together, you get like 1 trillion tokens, right? So in some sense, because these large language models are crawling through massive amounts of data, they have to be able to account for so many tokens. So their models have to be able to, understand and recognize so many tokens, right? And if you ask, this simple question, let's see. Sorry. How many books do 1 trillion tokens correspond to? Any guesses?
A million.
Million books. So one book is roughly 50,000 tokens, right? Like if you just count the number of words and then break it up and stuff. So if you just make a rough calculation, one book could be 50,000 tokens. So 15 million books would be equivalent to 1 trillion tokens. So the amount of information that, if you think of it this way, what makes a large language model a large model? Part of it is the amount of information consumed for training it and for it to understand and parse whatever kind of question you might ask. Like if anyone can ask any kind of question, coding question, math question, weather question, I need to have a massive terminology, right? Massive understanding of different concepts. And so 15 million books is roughly, you know, the equivalent of the data that a large language model with 1 trillion tokens would see to train itself to understand those tokens and also respond with a language model sitting on top of it. So tokens are just one part of it, right? Tokens is just like my vocabulary. But the real thing is to be able to parse, understand, and respond to questions that use these tokens, which is basically any kind of question. So that's what makes a large language model large is not just the parameters in the model, but also the amount of data, like in this case, 15 million books. You kind of gone through 15 million books and understood or derived information from there to inform your model and then make predictions. Yeah. So let's look at one more high-level thing before we start diving into some of the foundations. Is what are some ChatGPT use cases for NLP, right? For natural language processing. This is taken from one of the papers. If you look at the use case, and this is a little bit old, like maybe 1 or 2 years old, but it doesn't change a lot from year to year. So most of the use cases are in generation. You just want to generate a paragraph, a response, an essay, this or that, right? And then there's open Q&A, like just ask questions and get responses. The generation could just be like, talk about this. It doesn't have to be a Q&A, but so it kind of is a broad category. And then you have brainstorming. Let's brainstorm about, I want to brainstorm about this topic, right? Chat, rewrite. Can you rephrase the sentence? Can you reconstruct? Can you kind of format it better so a lot of people use it for that summarization, classification, etc., right? So here's some examples of brainstorming, generation, rewrite. So, but I would argue that these are generic use cases. If you look at the context of industry, there's many more use cases, right? Companies, like annotation is a major use case, like annotate my data. Like every company has data, and one of the biggest problems every company that wants to use AI or machine learning is how do you annotate your data? Like if a data is useless if you don't annotate it, because annotated data tells you or guides you on how you want to respond or how you want to behave. So if I don't have that guideline, I'm not able to use it as well. So, and LLMs, like we saw yesterday, LLMs can help with annotation if it's set up right. So, augment human annotation with AI-based annotation. So that's another use case in the industry. Any other use cases? Yeah, I mean chatbots as well, right? I mean even shopping assistants, right? So you have assistants of different kinds, shopping assistant, this assistant, that assistant helps you with different questions, and so that's a separate category. I would say the difference between chat and an industry specific chatbot is an industry specific chatbot is like very task focused. It's like very task oriented. It says like, I want to do really well on this particular task, like a shopping assistant. And like we saw yesterday on Monday, it needs to have guardrails on what it can respond to and what it cannot respond to. Like a shopping assistant should not be giving out dating advice, right? We saw an example of that on Monday. So that's definitely a big use case here. Maybe even recommendations, I would say another category that comes up in e-commerce companies is recommendations. Can you recommend certain products to customers? Although there are non-LLM based recommendation models, the use of LLMs in the space of recommendations is a new topic. It's evolving. People are seeing how it can benefit, right? Okay, cool. Any other use cases that comes to mind especially in a industry context?
I'm curious. I have seen a lot of stuff about agents, like being multiple agents being spawned to communicate with each other to solve a problem. Is that just a curiosity because it's fun and that's why it keeps getting recommended to me, or is that a serious pursuit in the field?
Where is it recommended to you? Sorry, I don't know the context.
Like on YouTube and stuff. It's like 20 agents. One is assigned a programmer role, one is assigned project manager, one is assigned code reviewer, that kind of thing.
I mean, I don't know about that specific example, but multi-agent systems is something that a lot of companies are going towards. And the reason is you can isolate issues with a specific agent. Like instead of saying you're the only agent that does everything, that might be too much to ask and may not be practical and might go out of hand. You can break up agents and say, you do this task, and then we'll make sure you have your own accuracy and performance measures. And the same goes for everyone else. And then if we notice certain agents are not performing as well, then you'll have to work on or replace or substitute it with something else. So it just helps with understanding points of failure in the system, right? Not having like a single point of failure, but being able to isolate issues. So agents doing specific tasks make a lot of sense because you can have a way to, and you can also understand where you need more time and which is more complex task and which is like a simpler task. So that also helps differentiate, and that's the reason like a lot of companies are going towards multi-agent systems. And also another advantage of having agent-based LLMs is that is the idea of reusability. Like I may not want to use like all the 20 agents that your team produces, but your one or two agents make a lot of sense for me. If you can just isolate that and then make it shareable, I'll just build on top of what you already have and then build my own agents on top of that. So it's also the idea of reusability of agents for specific tasks that make it, make it very appealing in an industry context.
I guess the simplest version is Watchdog versus the main one, which is already in use. So
yeah. 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 So I think agents is here to stay. And also, there's also the idea of like it could be that you are solving one business task, but there are multiple agents sitting behind it, and you need a way to coordinate these agents as well. So you might have a super agent that's kind of like managing or figuring out which agent to call for a specific subtask involved in your application. So um, you could also have those scenarios come up in multi-agent systems. And one of our mini projects has to do with multi-agents. So we'll all get hands-on experience with working with different agents that do different things. Okay. So it's 5:10. So why don't we take a 5-minute break? You can get some water or use the restroom, and then we'll come back at 5:16. So 5 minutes. Okay, so we covered some of the research, understanding of the use cases of ChatGPT, and then we also spoke about industry use cases. So now what we'll do is we'll dial back a bit. So we've been at the very high level, right? We spoke about motivation. We spoke about um, uh, the context behind LLMs and the history. We spoke about GPTs, all at a very high level. So now we'll go into the details. So let me switch to a different slide deck. So we're looking at part 2 of this lecture, and we covered the high level on LLMs, and we're going into some of the details, and we'll start with some of the foundations. And instead of going all the way back to machine learning foundations, we'll start with deep learning as a foundation, right? So we'll go with deep learning, and then we'll cover deep learning today, and then the next lecture. we'll go into transformers, and then we'll get to all the other abstractions on top of transformers like LLMs and other things, right? So today is mostly just like motivation for deep learning, and looking at some of the fundamentals of deep learning as well. So some of the history, some of the initial models, logistic regression, deep learning models, activation functions. Let's see what else is there. It's a lot. Okay. Activation functions. We'll see if we have a time for demo today. Training and backpropagation, overfitting, hyperparameters, and other deep learning architectures. Yeah. So if you have taken a deep learning course, then these should be familiar, right? So this is part of a deep learning course. If you have not, then this should be a good introduction. Even if you've taken it, I would say like you already have seen activation functions before, then maybe go a little bit deeper in this course, right? Understand it in a deeper way. So that's what I would suggest. Let's look at, yeah. So one of the good reference I would suggest for deep learning is this book on theory and fundamentals of deep learning. It's a book by Goodfellow and Benjo et al. So you can kind of take a look at it. The link is provided here. So deep learning, has had a lot of buzz I think this is also outdated, probably the past 2 decades, right? There's been a lot of buzz, and of course that's led to transformers and that has led to LLMs. So we're looking at this kind of this layer. And deep learning basically refers to neural networks. That's a loose approximation of how the brain works. Yeah. Like we still see a lot of applications of deep learning today, like self-driving cars use deep learning, right? Sentiment analysis, text summarization, arrhythmia detection, image to text generation, machine translation, autocomplete, and many more. Chatbots, yeah. So of course, some of these things apply more from a standpoint of LLMs, but I'm talking about deep learning as like a foundation model. It does apply. I mean, even an LLM is a deep learning model, right? It's like a deep neural network model. So if you think of LLMs as well, they're a deep learning model. So we're looking at the foundation. So email autocomplete, many of us use this, right? In Gmail or any other email application, you type in a sentence and then it autocompletes. And sometimes it autocompletes in real time and it does a good job. And it'll not just give you one, sometimes it gives you different suggestions as well. So those are like the probabilistic predictions coming out of a deep learning model, right? Image to text. This is like a lot of vision research has gone into computer vision, has gone into like making these things more and more accurate using large vision models like image segmentation, like understanding an image, describing an image, et cetera, et cetera. So a lot of it has, like initially vision models were not based on deep learning, but now it's completely based on deep learning and you can see they're doing a very good job, right? So this is one example. Arrhythmia detection, just wanted to give this as a different kind of example for deep learning is, and I think we covered this in one of the, I think maybe the foundations of machine learning course, is that this is a form of anomaly detection, right? The main machine learning task here is anomaly detection. right? So the only thing is the anomalies are very sophisticated. So for instance, these are what we call point anomalies, right? So why are these point anomalies? Because anomaly is any data point that kind of goes off track. So as a point, this point is going off track, right? Because maybe if you want to draw the, let's say this is the mean, right? If you say mean plus standard deviation or something, you might say, okay, mean plus 2 standard deviations is this, right? So 2 standard deviations this way, 2 standard deviations this way. So you say for any given time series of data, I can compute the mean and I can also compute the standard deviation. And typically you say mean plus or minus 2 or plus or minus 3 standard deviations kind of captures most of the data. So point anomalies would be like any point that falls outside of this, right? So for instance, anything this way or this way would qualify as point anomalies. So you can see all these things stand out as point anomalies. But arrhythmia detection is a very interesting use case because you can't just detect point anomalies and say, this is arrhythmia, because arrhythmia is about a chunk of time where the heart behaves anomalously, right? The beats look different as a chunk of time, right? Not just as a point. So in this case, let's see if I can use a better color. Yeah, okay, cool. Let's look at, let's use this one. Okay, so if you look at this, right? So this chunk is an arrhythmic heartbeat. Do you see why? Any given point in this chunk is not a point anomaly. There's nothing, it's not going off limits, but as a chunk, it looks a different pattern from, let's say, this one or from this one. Like these look normal, but this looks arrhythmic, right? So this tells us that we need more sophisticated machine learning to be able to detect arrhythmia rather than just a simple mean plus standard deviation rules or simple point anomaly detection. So when you want to detect sophisticated patterns that are nonlinear and understand them as arrhythmia, that's where deep learning would help. So in this case, deep learning would say, I know these all look normal, but as a chunk, there is something off about this particular thing. And so if you use an app that detects arrhythmia, that measures your heart rate, it might be deploying some deep learning model and saying, hey, in the last 15 seconds, you had an anomalous heartbeat. And I think there is some arrhythmia that I'm detecting, right? So a lot of apps these days, like they track your heart rate. Like how many of us use some kind of a ring or some kind of a smartwatch that kind of does these things, right? Like many of us might be doing that, using it, right? And you'll see like they are getting really good at detecting sophisticated things like even sleep apnea. Like I think that you can detect sleep apnea, you can detect anomalous heartbeats. You can, of course, you can also detect the sleep cycles if you're looking at sleep. But some of them are straightforward and some of them are not. Some of them require, some of them are just rules of thumb, right? Like just if this is true, then this is happening. Others like this one require a more sophisticated AI like deep learnings, right? So this is a very good example of why deep learning in this case would look at the pattern and say, hey, I want to look at the sequence, and the sequence in some sense is anomalous to any other sequence. And so then a deep learning model would take this chunk and say it's anomalous, and then it take this chunk and say it's normal. So that's how every single minute you would kind of look back, maybe the last 1 minute or so, or last few seconds and say there was an anomalous heartbeat or it is normal. So that's how an app would probably use it. So anyway, so we just did a little bit of deep dive here. And you can think of many other applications where deep learning get used. Okay, so brief history of deep learning. 1965 is when one of the first deep learning models came out by Ivak and Co. They didn't use back propagation for training, but used some other objective like sequential least squares fit. The earliest convolutional neural network was by Fukushima et al. In 1979. The earliest back propagation, which is kind of the backbone, right? This is like the backbone to train a neural network. It's actually now become standard. Like you need to use backprop for neural networks, deep learning, even pre-training foundation models, anything that has like neurons in there, or any sophisticated transformations that involve networks, you'd want to use back propagation. But the earliest instance of that was in 1985, right? And earliest application was to recognize MNIST handwritten digits by Jan LeCun. So Jan LeCun, Joshua Bengio, and then there's a few more people who've kind of like become the founding fathers of deep learning, right? And one of the earliest nets, so we have a lot of nets that came in deep learning, right? So deep learning was characterized by nets like LayNet, AlexNet, convolutional net, and so on. So one of the earliest nets was also 1993. And this was the beginning of X nets, where X could be AlexNet, Inception Net, this net, that net, right? But even though these came out in 90s, they were still not considered usable by most people. People thought, hey, this is nice as a concept, this is nice, but we don't have the capability to actually harness the power, so it's not practical. So people actually dismissed neural networks in 1990s. So although all these developments came about, people said, hey, yeah, we're not going to use neural networks, we'll use something else. So people were hesitant to use, like, we'll use hidden Markov models, we'll use some other model, we'll not use neural networks, right? And even the discovery of recurrent neural networks like RNN and LSTMs happened in 1997, but they were not harnessed until later, right? So what happened between 1997 and 2006 is GPUs got faster, like 1000x computational speed improvement. Like things that would take, thousands of hours can just take like 1 hour. So you really are speeding things up, and you can churn a lot of data, and you can learn faster, you can train models faster. And so yeah, so there's a lot of innovations that started happening starting in 2011, right? So there was this competition called ILSVRC competition for vision that had a big image-based data set, and researchers were asked to keep improving on image. So a lot of vision work happened between 2011 and 2017. So this is a period where deep learning based vision models improved quite a bit. And then 2017, language also came along. So before this, we still had LSTMs and recurrent neural networks. These were still used in this period, right? 2010 to 2017. In the meantime, vision had improved quite a bit. So before 2011, for any image applications, people were like, we don't want to use, we don't have to use deep learning. We'll just use standard computer vision. But 2011 to 2017, with this ILSVRC competition, it changed everything. Like people started using deep learning everywhere, and the vision community, they simply didn't accept deep learning. They said it's not true. It doesn't make sense. We've been working on vision models for 10, 15 years, and you come along and you say deep learning will just help. We don't buy that. So people refuse to believe that deep learning can have an impact. But then with this competition and more papers coming out, the computer vision community embraced deep learning and said, yes, okay, deep learning makes a lot of sense now. And the same happened after transformers came into the scene. There was a language model revolution, right? So 2017 was when it started with this paper, Attention is All You Need. So lot of improvements happen on transformers side, and ChatGPT came out 2022, ChatGPT 3.5 came out, and then that's when people started to notice AI. Until then, AI was interesting, but not really something that you would want to connect with. But after 2022, AI was put on the map, right? And there was some cross collaboration between language and vision too. So transformers, which was mostly a language model, also got applied in vision, and then came out an architecture called V transformer. So vision transformers. So you can apply transformers to vision. So people applied one architecture from language to vision, and they saw things can help. So all those things happen, right? And more is happening between 2022 and 2024, much more that we'll probably cover in more in future lectures, right? So there's a lot more that's happened as well. Um, but yeah, I think it's very interesting. I think this is like kind of one of the key things is GPUs got really fast, and you can actually churn and train over massive amounts of data, and you can train on large networks. So previously, if you had like millions and millions of parameters, forget about training. It just takes too much time to train and you would overfit. This was the understanding. But with deep learning, people saw that you can keep feeding in more data and it'll do better and better and it won't overfit as much. And so there's something about deep learning that became very appealing once you had the resources like GPUs to do the training, right? So it's very interesting. Like a lot of things came together to put deep learning on the map. Okay, so that was another brief history that we went through. Let's now dive into like a single cell perceptron, right? Let's start looking in the foundation fundamentals, um, and see how we went from perceptron to logistic regression to deep learning, right? So perceptron is simply, like we said, it's a single cell neuron, right? So you take in inputs. So it's a perceptron. You take in inputs, you do something with it, and then out comes the output. So these inputs could be, you can characterize it as x1, x2, x3, and so on. Let's say xt. So there's like d inputs. And then corresponding to these, you have w1, w2, w3. These are the weights, right? So w transpose x is w1 x1 plus w2 x2 plus so on w dxt. So these weights are what we learn, right? So x's keep changing, right? Because that's your data, but the w remains the constant. So you learn the w. So the weight is what gets learned in training, right? So here's a more graphic representation of perceptron. You have x's, you have w's, and you have a sigma function, which is multiplying and then summing it up. And obviously you have an intercept here just to account for, uh, like sometimes, if your data is like, let's look at an example. So if your data looks like this, so then your W transpose X looks like this. So you can see this is not passing through the origin, right? So this is W and the W transpose X. So since it's not passing through the origin, we need this intercept. Yeah. So and in this case, you could have like, I mean, as an example, these could be like cats, and then these could be like dogs. So here the task is uh, discriminate cat images from dogs. I mean, just as a simple example. So let's say the task was discriminate cats from dogs from an image. You get an image, is it a cat or a dog? And all the yellow points are cats, all the green points are dogs. And so the perceptron would learn this line, W, that kind of differentiates the two, right? Because if you had some other line somewhere else, let's say I had a line here. Is this a good discriminator? No, because it says everything is a dog, right? Because anything on this side is a dog. So even cats are classified. So this is not a good one, but this is a good one because it's able to discriminate and differentiate the cats from the dogs. So learning the line that differentiates these data points is basically what a perceptron would do, a binary classifier, right? So the perceptron, there's one thing with perceptron is it's more theoretical than practical because the way it does discrimination is it uses a step function. You basically say uh, if so you this W transpose X becomes a score, right? So you score every data point. So you get X, and then you have a score, which is W transpose X. So you have something else, like let's say X2, you have W transpose X2. So I score every single data point. So this is my data. So let's say maybe this is a cat, and then this is a dog. So X is a cat, X2 is a dog. Okay. I mean, we're representing an image in some way in the data. So then you score this, and then you say, okay, if W transpose X is greater than 0, then call it a cat. And if it's less than 0, you call it a dog. Okay, so this is good. But this is a step function, and it's abrupt, right? So it's not smooth and it's not differentiable. And so, but but in principle, in theory, it does the job because this is what you want to do. You want to differentiate two classes, you can do that. So a modification on that is what we call the logistic regression. So perceptron is theory, logistic regression is practice. How do you take something that's theoretical and make it an algorithm? That's what logistic regression does, is you go from perceptron to logistic regression. And logistic regression is it's like a one-layer neural network. So it's the simplest form of a deep learning model. It's actually not deep learning, it's shallow learning, but it's like just one layer neural network. And the simplest algorithm that came out of perceptron-based model is logistic regression. So what logistic regression did is it took the step function that's not differentiable and replaced it with sigmoid, right? So sigmoid is more continuous and smooth. And sigmoid gives a probability. So you get a probability from 0 to 1, but a step function gives you 0 or 1. It's just like very hard thresholding. So this is not easy to differentiate or train on, but the sigmoid is. So that's why logistic regression is a model that made perceptron more practical, right? So we started with perceptron, we went to logistic regression. And then you get a probability score. And the probability score tells you if the score is high, then the probability is high. And then you would classify it as a dog with high likelihood. If the score is low, then it would be, the probability would be low, and you would classify it a different way. So not only are you able to classify, you're also getting probabilities here, right? Yeah. So as you can see, we went from very high level to very detailed. So this is how the class is going to be. Sometimes we're going to be at very high level. Sometimes we will jump into the details as needed, right? So right now we're jumping into the details. So the fundamentals of logistic regression, it's a linear model, right? Why is it linear? Because it has this W, and you take a linear combination of the data. So this is a linear combination of weights and data. And you can see here, when you represent it, it's a linear. So this is a linear separator. Right? Okay. And there's another concept with logistic regression is like the data itself can be linearly separable or not separable. So logistic regression is one of the simplest machine learning models that we should all know about. And it works when your data is linearly separable. If it's not as separable, it's all meshed up, then forget about it. It's not going to work. So it works in certain cases and it doesn't work in other cases, right? Yeah, we spoke about probability for a class. And we said that instead of step function, we use a sigmoid function. So the way the scoring happens is you just say the probability of it being a cat or dog, right, is 1 over 1 plus e to the negative w transpose x. So let me just do. So probability of x is a cat equals this, right? So this function is a sigmoid function and it's always between 0 and 1. And we know probability is always between 0 and 1, right? So probability cannot be negative, probability cannot be more than 1. So the sigmoid function makes sure that the probability is always between 0 and 1, right? Great. So logistic regression is good for doing certain things, right? Theoretically, you can differentiate an OR, you can differentiate an AND, or learn an OR function, learn an AND function. And when you look at how the graph looks like, OR is 0, 1, 0, 1. Let's say is x, y, or let's say x1, x2. x2, x1, right? So if it's 0 and 0, what's OR?
0.
0, right? So let's say x is 0 and this is 1. So this is 0. 0, 1 and 0, OR is
1.
1. 1 and 0, OR is 1. 1 and 1,
1.
Yes.
1, right? So if I draw a line like this, can I differentiate? Can I learn the OR function?
Yes.
Yes, right? Because I'm able to discriminate the ones from the zeros. So any function in between can actually do this job, right? So you can even have something that's here, and that also learns the OR. But then if you had something, get something here, so this doesn't learn the OR because it's saying, because it's going to classify everything as a 0. But this one will classify it as 1 here, and it'll classify as 0 here. Does that make sense? And the same goes for AND, right? You can also learn an AND function. This is a very simple example. But if you come to XOR, can a logistic regression learn an XOR? So what is XOR? So again, let's say this is 0 and then this is 1. So 0 and 0, what is XOR?
1. 0.
0. 1 and 0?
1.
1. 1 and 1?
0.
0. And 0 and 1, 1. Yeah. So now the question is, can you draw a line in this graph that can separate the ticks from the crosses?
No.
No, right? So suppose I draw a line like this. Does it separate the ticks from the crosses?
No.
No. If I draw a line like this, does it separate the ticks from the crosses?
No.
However you draw, I'm not able to separate the ticks from the crosses. Do you see that? You can draw it however you want. I can draw it here. Sorry. So I can draw it, you can draw it here, I can draw it here. No matter what I do, there's no way to linearly separate the ticks from the crosses. Do you see that? So this is an example where you can learn OR, you can learn AND using a logistic regression, but you cannot learn XOR. There's a fundamental limitation. So there's a fundamental limitation of using a single neuron. In this example, a single neuron can learn an OR, it can learn an AND, but it cannot learn a XOR, right? So just to summarize, single neuron, which is perceptron, It's logistic regression, it's all the same thing. Let's see. So OR and XOR, right? So you can learn an OR and, but cannot learn an XOR. So this illustrates the need for, and XOR is a simple function, a simple nonlinear function, right? But the world is so nonlinear, like differentiating cats and dogs, differentiating this from that, differentiating trees. So, here's another example. For a self-driving car, have you noticed in the initial versions, it would say a tree is a person is a tree. Have you heard of those examples? A truck is a car is a two-wheeler, a stop sign is something else. Have you heard of examples of those? Yeah. So those are complex nonlinear objects that require very high level of discrimination. And even though a self-driving car uses deep learning models, it can still fail because the objects to differentiate are so complex, right? So if XOR is complex, imagine differentiating a tree from a person or pedestrian or whatever, right? Those can become very, very complex for these models. And that's why we need to move from a single perceptron to multi-layer perceptron. And that's the motivation for moving from a single layer neural network to a multi-layer neural network, right? So in the next class, we'll actually look at this. XOR can be learned through a multi-layer perceptron. Like we exhausted all possibilities for a single layer perceptron, right? So clearly, single layer perceptron or logistic regression fails for XOR, right? But XOR can be learned through a multi-layer perceptron. And we'll look into the details of this in the next lecture, right? And we'll continue on down this path. It's a very interesting, I think, and this is good because I would love for you guys to work on this in person. And since the next lecture is in person, I think this is a good place to stop. We'll dive into how XOR can actually learn, it can be learned through just two layers, and then you have like multiple neurons here, and then it does its job, right? So we'll go into that in the next lecture. And there's much more to cover. Yeah, there's many more things. So we have more deep learning stuff to cover. We'll do that in the next lecture, and then we'll continue. Okay, I'll stop here. If you have any questions, we have some time, but we're also at time.
Thank you.
Okay.